Channel. Today we continue with the textbook that we have been reviewing, which is the Modern Computer Vision with PyTorch. I highly recommend the book, and we shall be looking at implementing feedforward propagation, the lecture 5. So now, in the last time we talked about the neural network, and implementing a neural network requires two phases: the feedforward and the propagation, backward propagation. Now in the feed forward, you start from the input and you go to the output. In the backward, you start from the loss, the estimated loss, and you propagate that back into the network. So the name feed forward is derived from going forward. So here they're using a typical example of a network that has just an input of 1 on 1. You represent this input as a vector. So let's say you have this vector of a column vector of 1 1. In the ideal case, this will be a tensor, a n-dimensional tensor with multi-dimensional arrays. So for simplicity, we're just using a column vector as our input. So now here, to do a feed forward, this is a fully connected, is it really fully connected? Okay, we can say the input is fully connected to the hidden layer. You see, all the inputs are connected to the succeeding neurons that we have here. Okay, so what is happening here is in each of these edges, so in graph theory, we refer to each of these as a node. So this is a node, each of these is a node which represents our neurons, and each of these edges contains the learnable weights. So those are actually the weights that we want to learn, the learnable weight, the weight of the neural network that we want to learn. Okay, so that's the weight. That's an important concept. So that's the weight of the neural network. Now, so which essentially is a floating point value. So we keep adjusting this until we get a right set that is optimized for the task at hand. That is the one that brings our loss as close as possible to 0. So the flow of the pipeline, the process is we calculate the hidden layer values, we perform nonlinear activation, estimate the output layer, then calculate the loss and use that loss to optimize the weight. So let's see how we calculate the hidden layer unit value in this particular scenario. The first thing we do is, first of all, we don't know what the values of the weight are. So what we do is that we randomly initialize this to a particular, we initialize it, I hope this copies, it doesn't. We initialize this to a random set of values. In literatures, good, it copies. In literatures, you are always advised that you initialize it such that the mean will be 0 and I'm sure we should be able to see this. I'm trying to expand this. Oh, bad. Sorry about that. Let's see whether it can be expanded. Is it good? Okay, good. So we initialize it in such that the mean is 0 and the standard deviation is 1. So you normally represent standard deviation by 1, and mu, which is the mean, you represent it with 0. So these values, when you sum up all the values and divide by the total number of edges, you expect that it gives us a mean of 0 and a standard deviation of 1. That is essentially what you normally have. So you have something like this. it's where you have the center and it's centered at 0, and the distance between here and here, which is 1 standard deviation, is 1 here and -1 here, so 1. So that's essentially what we refer to as normal distribution, n, normal distribution n. Okay, so but here they're just using some values. Let's just say we give 0.8 to the edge between here and here, and 0.4, here is 0.3, here is 0.2, here is 0.9, here is 0.5. So you just give some random values to all those ones. Now that is initially. So what we now do is that we use those random weight that we have put there to calculate the values at each neurons. So if we represent each of these as H11, H12, H13, so we first of all calculate the value before activation. Activation is just a function before we apply the activation function. That is represented with H11, and H11 has this formula: just multiply the input multiplied by the weight. We have excused the bias in this example just for brevity. So you just take, to calculate all the H11 for this, you multiply all the incoming edges with their respective input. So W11 multiplied by X1, W12 multiplied by X2. So that's why we have our H11. You do the same thing for H12, which will be the edges coming in at W12 and W22, and you multiply that by their corresponding input X1, so that's why we have this, and X2, that's why we have this, and you multiply that. Don't forget our X1 and X2, they are 1. So by the time you do that, you get H1, H12, H13 as these values: 1, 1.3, 0.8. Essentially, you process this as a column vectors too. So 1, 0.3, and what is the third one? That is 1.3 and 0.8. So 0.8. So you process this as a column vector, just to make sure it's optimized, to be able to have an optimized input for your GPU processing. Okay, so these are the activation, these are the value, the hidden layer unit values before activation. Then we can now apply activation function to each of these. So when you apply the activation function, there are different activation functions we could apply, which will be, it could be linear, that means you are not putting anything, sigmoid, ReLU, and tanh. Don't forget that once you have these values for each of these hidden units, you do the same thing also for this. You do the same thing to be able to calculate the output for this layer, because here we have randomly initialized this to 0.3, 0.5. So the values that we got from the preceding layer, we're going to multiply that again. So we'll be multiplying 1 by 0.3, 1.3 by the, but you need to first of all decide which activation function you want to use on this before you do the next phase processing. So as you can see here, we're introduced to the different activation functions and their formulas. So here we'll be using the sigmoid activation function. So the H11 has 1, then we pass it to the sigmoid, and it gives us 0.73. Look at the formula for the sigmoid. The x is just 1, so here our x is representing all these 1, 1.3, and 0.8, and that can give us this. Then we do the same thing for the other values, and we get these values. So these values are now the values after activation. That's the value after activation. So upon getting the values after activation, we repeat the same thing again now to be able to arrive at our output layer values. The same thing is repeated, so you multiply 0.3 by the output, the value that we got after applying to the sigmoid activation function. You do the same thing here and you do the same thing here. Now our final value is now 1.235. So that means our network predicted 1.235 as the continuous value, because in this case we are predicting a continuous variable. That means the number could be infinite. So it is not discrete, it's not categorical. So, and what we're expecting according to our problem specification is we want a network that will take in 1 1 and it will give us 0 as our input. That is what we want. So the input is 1 1 and the output we want it to be as close as possible to 0. That's our objective function. But what we got from our network is that the network is getting 1 1, and because we initialize the weight randomly, it is giving us 1.235. That is far away from our desired value. So what do we do then to be able to make sure the network is forced to be able to give us a prediction that is 0 or close to 0? We do that by calculating the loss values, and that is where we'll continue in the next one. Thank you, and see you next.